Hi, everybody. This is Chen Guangzhu from Microsoft Cognitive Services Research. Today, I'm going to introduce our work on leveraging lead bias for zero-shot abstractive news summarization. This is joint work with Ziyi Yang, Robert, Michael Zhang, and Xuedong Huang. Lead bias is a very common phenomenon in news articles, and it is aligned with the journalistic style that early parts of a news article often contain the most salient points in the whole article. Although lead bias facilitates reading for humans, it actually hinders models to learn what is the truly important information in the article. And many summarization models, after learning on news summarization datasets, often learn to just extract sentences towards the beginning of an article. And there has been studies that show that if we randomly put these top sentences into random positions in the article, the model trained on these datasets will perform less well. Here, we visualize lead bias in 5 news article summarization datasets. On the x-axis, we show the normalized position of a sentence in the article. And on the y-axis, we show the ratio of words in this sentence that are also present in the reference summary. And as you can see, there is a strong lead bias in 4 out of the 5 datasets, except XSUM, where the ratio is very high towards the beginning of the article, and it decreases towards the end. While lead bias has been an obstacle for training summarization models, in this paper, we argue that we can take advantage of this lead bias in our favor. The reason is that we have many news articles without reference summaries written by humans. So here we can use the lead bias to treat the first few sentences as a surrogate summary. So we have free labels for the summary. Here's an illustration. Our task is to predict the summary, for example, the top 3 sentences using the rest of the article. We call it rest. Because in the whole process, we need no human labels at all, we can leverage the millions of news articles online to conduct self-supervised pre-training. To collect the data, we use the public online news articles from June 2016 to June 2019 via the index of the Bing search engine. And then we did some simple filtering to make sure that the lead 3 and rest contains enough information. However, although lead 3 is common, the lead bias is common in news article summarization. Is lead 3 for a particular article always a good summary? Definitely not. So here we want to find some simple criteria by which we can filter the articles. So we propose to use the portion of non-stopping words in lead 3 that are also in the rest of the article. Our hypothesis is that a higher portion implies that lead 3 is more relevant to the rest and has a higher chance to be a good summary of the rest. So there are 2 questions. First, is this hypothesis true? Second, even if this is true, what threshold should we choose for this portion to filter good summaries? Let's let the data speak. Here, we look at the distribution of overlapping non-stopping words between different parts of the article. We have 3 things: the reference summary, the lead 3 or the top 3 sentences, and the rest, where the lead 3 and the rest make the article. First, we look at the distribution of overlapping ratio of non-stopping words between the reference summary and the article. That is, how does the ground truth label get this distribution? As you can see by this red curve, it does have a high ratio and towards 1. So this proves that our hypothesis is true. Secondly, by this green curve, we show the ratio between the reference summary and the rest, because ultimately we want to use the rest to compute this ratio against. So this is also high, although not as obvious as the red curve. And finally, we check the ratio between lead 3 and the rest, which is the ratio we will compute and the criteria to use. So here we see that the ratio is generally lower. Thus, if we want to pick articles where lead 3 can be a good summary, at least in the sense of ratio of non-stopping words, we should filter out all those articles where this ratio is lower than, say, a 0.7, so that the rest article we get will have a similar ratio as the true ground truth label. In the end, we choose 0.65 as the threshold of overlapping non-stopping words between lead 3 and the rest. All articles with a ratio lower than 0.65 are thrown away. This is to strike a balance between the quality of the data and the amount of data we get at last. In total, we filter out 95% of the collected news articles and end up with 21.4 million articles for pre-training with 14.2 billion words. For the model, we choose the BART large and T5 large as a starting point, and then pre-train this model further on our data sets, and we call the ending model as BART LB and T5 LB, standing for lead bias. An important contribution of our work is that we will use these models directly on downstream tasks without any fine-tuning. In other words, our models do not need to see any single human labels. But here we highlight the difference between various summarization methods. Supervised summarization needs to have access to both the articles and human summaries in the training data to fine-tune the model. Unsupervised summarization, although indicated by the name unsupervised, still needs to have access to training articles to get a sense of what the distribution of the word is. But zero-shot summarization, which is our work, needs no access to the training data at all. So after the pre-training, it will be directly used on various new summarization data sets. This will be better and more easily applied to real scenarios. Here in this table, we show the main result of our summarization model BART LB, T5 LB, and the baselines on 6 summarization data sets. We characterize these models into supervised, unsupervised, and zero-shot groups. Firstly, we see that our models achieve the new state-of-the-art in the zero-shot category by a large margin. And particularly after the pre-training, BART LB improves the result of BART large by a large margin, and similarly, T5 LB improves T5 large. Secondly, even comparing with unsupervised summarization, we outperform them in many data sets. Finally, if we compare our result with the lead 3 baseline, we see that we outperform the lead 3 baseline in 5 out of 6 data sets. In other words, our model goes beyond just merely copying the top few sentences from the article. The reason is that during training, our model only sees the rest of the article as a starting point and then try to generate a target, which is the top 3 sentences. So it will be very rare that the top 3 sentences of the rest will be still similar to the top 3 sentences. One question people may have is whether after this pre-training using lead bias, our model just learns more lead bias. It turns out that it's not true. So here we evaluate the abstractiveness of generated summaries via the percentage of novel n-grams, or the portion of n-grams in the generated summary that are not present in the original article. A higher ratio indicates a higher abstractiveness. As you can see, after the lead bias pre-training, this orange bar is generally higher than the green bar, which is the model before the pre-training. So it means that our lead bias pre-training can help the model improve their abstractiveness, which is generating appropriate words and phrases that are not in our article, but are good at summarizing salient points in the article. And if we further fine-tune the model on supervised training, this ratio will further increase. We also conduct human evaluation on the quality of the generated summaries of our models and the baselines. We evaluate the readability, which measures how fluent and how grammatical the summary is, and also the relevance, which measures whether the generated summary can summarize the salient points in the article. As you can see, after this zero-shot pre-training, the BART LB and T5 LB significantly outperforms the starting point BART large and T5 large. And while the lead 3 sentences have a very high readability because they merely just copied the first few sentences of the article, their relevance is not as good as the BART LB and T5 LB. We also conduct error analysis to see where our model get it wrong. We see that the most common reason for errors is that the summary contains insignificant information from the article. And actually, this is also common in supervised and unsupervised summarization models. And other reasons include invalid co-references in the summary, incomplete sentences, especially at the end, and so on. Finally, our model has been shipped into Microsoft News to provide summary for news every day. And Microsoft News has also helped us establish a demo website, which includes multilingual summarization and voice-based summarization, and a public API for developers to directly call to get summary results. Okay, that's it. Thank you very much for listening.